Our final outcome is about probability distributions, the models we use to describe real-world uncertainty. We'll meet both discrete distributions, where we count, and continuous ones, where we measure and learn to recognize which one fits a given situation. Here's what we'll cover. We'll start with discrete random variables and how to describe them, then look at the discrete uniform distribution. Next comes the binomial distribution, written B, NP, along with its conditions and its mean, NP. After that, we'll turn to the normal distribution as a continuous model and practice recognizing real situations where each of these applies. Let's begin with random variables. A random variable assigns a number to each outcome of an experiment, and we usually write it with a capital letter, like X. A particular value it can take gets a small letter, X. For instance, if X is the number of heads when you toss a coin twice, then X can be 0, 1 or 2. And the notation, the probability that X equals X, just means the probability that X takes that particular value. There are two families to keep apart. A discrete random variable takes separate countable values, often whole numbers like 0, 1, 2, 3. Think of the number of faulty items in a box, and we list its probabilities value by value. A continuous random variable, by contrast, can take any value in a range. It's measured rather than counted, like height, time, or mass, and there we find probabilities over intervals rather than at single points. For a discrete variable, a probability distribution is a table or rule listing each value alongside its probability. Two conditions always hold. Every probability sits between 0 and 1, and all of them must add up to 1. Together, these describe the entire behavior of X. Take X as the score on a fair six-sided die. Each score from 1 to 6 simply has a probability of 1/6. A few terms to set down. A random variable is a quantity whose value depends on the outcome of a chance experiment. Discrete means it takes separate, countable values, usually whole numbers. Continuous means it can take any value within a range, measured rather than counted. A probability distribution describes all the possible values and their probabilities. And a trial is a single repetition of an experiment, like one coin toss. The simplest distribution is the discrete uniform, where every possible value is equally likely. If there are n outcomes, each one has a probability of 1 over n. The classic example is a fair die, with a probability of 1/6 on every face, and a fair coin is uniform over heads and tails at a half each. Drawing a single card from a shuffled deck of 52 works too. Uniform essentially means flat. No value is favored over any other. Let's use it. A fair spinner has 5 equal sectors numbered 1 to 5, and we want the probability of a 4 and of scoring more than 3. With 5 equally likely outcomes, each has a probability of 1/5, so the probability of a 4 is 1/5, or 0.2. More than 3 means a 4 or a 5, which is 2 outcomes, so that's 2/5, 0.4. Where does the uniform model turn up in real life? Rolling a fair die in a board game, a raffle where every ticket has an equal chance, a random number generator picking a digit from 0 to 9, or drawing a name fairly from a hat. The one condition is that the outcomes must genuinely be equally likely. A biased or weighted item breaks the model so it wouldn't be uniform. Now for the binomial distribution, which counts successes across a fixed number of trials. Each trial has just 2 outcomes, which we label success or failure, and we write it B, NP, where N is the number of trials and P is the probability of success. The number of heads in 10 coin tosses, for instance, is B 10 0.5. We're always counting how many times something happens, and the result is a whole number from 0 up to n. The binomial rests on 4 conditions. There's a fixed number of trials, n, decided in advance. Each trial has just 2 outcomes, success or failure. The probability of success, p, stays the same on every trial, and the trials are independent, so one result never affects another. If all 4 hold, then the count of successes follows B, N, P. A handy way to remember them. Fixed, 2 outcomes, constant P, independent. Let's sort situations into those that fit and those that don't. Tossing a coin 20 times and counting heads fits, as does testing 50 bulbs for faults or asking 100 people a yes or no question, each an independent trial with a fixed P. It does not fit when you draw cards without replacement, because P changes, or when you count until the first success, since N isn't fixed, or when you're measuring height, or when there are 3 or more categories of outcome. Some terms for this section. The binomial distribution models the number of successes in n independent trials, written B, N, P. A success is simply the outcome you've chosen to count. P is the probability of success on a single trial, held constant across trials. Independent means one trial's result has no effect on any other. And the uniform distribution, by contrast, is one where every outcome is equally likely. Let's check a situation. A machine makes components and 5% are defective, and an inspector checks a sample of 20. There's a fixed number of trials, 20, so n is 20. Each component is either defective or not. 2 outcomes. The defect rate is a constant 5%, so P is 0.05. And whether one is defective doesn't affect another, so they're independent. All 4 conditions hold, so the count follows B, 20, 0.05. The mean of a binomial tells us the typical number of successes we'd expect. For B, N, P, it's beautifully simple. The mean is NP, the number of trials times the probability of success. So B, 10, 0.5 has a mean of 10 times 0.5, which is 5 heads, exactly matching the intuition that about half of 10 tosses land heads. And note, the mean needn't be a whole number. Here's a nice example. A multiple-choice test has 40 questions, each with 4 options, and a student guesses every one at random. With 4 options, the chance of a correct guess is P equals a quarter, 0.25. The number of questions is fixed at 40, and the guesses are independent, so it's B, 40, 0.25. The mean number correct is NP, 40 times 0.25, which is 10. So on average, they'd get 10 right. Another quick one. A factory finds 2% of its light bulbs are faulty, and we want the expected number of faulty bulbs in a batch of 500. The probability a bulb is faulty is P equals 0.02, and the batch size is n equals 500. The expected number faulty is NP, 500 times 0.02, which is 10. So you'd expect around 10 faulty bulbs per batch. Let's check your understanding. Can you state the 4 conditions needed for a binomial distribution? For B, 30, 0.2, what's the mean number of successes? And why is drawing cards without replacement not binomial? Have a think before you carry on. So far, we've been counting successes, always landing on discrete whole numbers. But a great many real quantities are measured rather than counted. Height, weight, time, temperature, and these can take any value at all. They call for a continuous model instead of a list of individual probabilities. And the most important continuous model of all is the normal distribution, which describes data clustering around a central average. The normal distribution is our continuous model for measured data. Its graph is a smooth, symmetrical, bell-shaped curve, with most values lying near the mean and fewer as you move out to the sides. It's symmetric about the mean, mu, and its spread is captured by the standard deviation, sigma. And, as with any probability model, the total area under the curve comes to 1. Let's look at the bell curve's features. Its peak sits at the mean, which for a normal distribution is also the median and the mode. The curve is symmetric, the left half mirroring the right, and it tails off gently on both sides without ever quite touching zero. A small sigma gives a tall, narrow curve with values tightly clustered, while a large sigma gives a low, wide one with values more spread out. The further from the mean, the less likely a value becomes. When might the normal distribution apply? The heights of adult men or women in a population, small measurement errors scattered around a true value, the weights of items off a machine, or the exam marks of a large group of students. The telltale signs are a single central peak, symmetry, and tails that fall away gradually. It suits natural, continuous data that clusters around an average. Let's recognize one. A tutor records the heights of 500 adult women and draws a histogram. It has a single peak near 162 centimeters, is roughly symmetric, and tails off gently on both sides. Height is a measured, continuous quantity, so we need a continuous model. The histogram has one central peak with values clustering around an average, and it's symmetric with gently falling tails, exactly the features of a bell curve. So the normal distribution is a suitable model here. Let's put the choice side by side. Reach for a discrete model when you're counting outcomes, uniform when the results are equally likely, like a fair die, or binomial for successes in n-fixed trials, and there the values are whole numbers. Reach for the normal model when you're measuring a quantity, continuous data such as height or time, that's symmetric with a single central peak, and clusters around the mean, mu. A final check for this outcome. Can you give two real quantities that the normal distribution could model? What two features of a histogram would suggest a normal model? And would you use a discrete or a continuous model for the time taken to run 100 meters? And why? Give those some thought. So let's draw the outcome together. Discrete variables are counted, continuous ones are measured. The uniform distribution makes every outcome equally likely, each with a probability of 1 over n. The binomial, b, n, p, needs a fixed n. Two outcomes, a constant p and independence, and its mean is np. And the normal distribution is a symmetric, bell-shaped, continuous model, fitting measured data such as heights and measurement errors.